BYP's third video on transmission lines and antennas. Unfortunately, it's necessary to go through tuned circuits and components because there is an appearance that antennas work by resistance and reactance is absolutely false. That's only the appearance at the feed point. It's useful in some ways, but modern antenna theory has proven that this idea of antennas being resonant and having reactances and all that is not that it's incorrect or insufficient, it's completely inapplicable. All that old theory has been thrown out and been replaced by actually modern nuclear theory, and it gets ugly. It's an extreme oversimplification to look at a feed point and say that an antenna is this and such. It isn't. But it's a start. And it's going to come up because it's been SOP for 150 years. So we may as well go through it. 3 components in electricity, R, L, and C. R, resistance is linear, dissipates energy as heat, voltage and current in phase. V, DC voltage equals I times R. V could also be AC voltage, I times R, with no phase shift. Power factor of unity, total loss. No frequency component. Resistance is not impedance. Resistance has no frequency component. Critical. Inductor. Voltage E is I, current, times X of L, inductive reactance. Omega L, or 2 pi F, which is radial velocity times the inductance, is the inductive reactance. Inductors store energy in fields, doesn't dissipate it. The inductor function is linear. Omega L is linear. Capacitor stores energy in an electrostatic field between the plates. E is a function of current times capacitive reactance. Minus X sub C, capacitive reactance is reckoned in series as negative or inductive as positive. Very critical point. That opposite behavior is why tuned circuits work. That's 1 over omega C. Omega is 2 pi F. 2 pi times the frequency. In a series circuit, we have a series resonance when X sub L magnitude and X sub C magnitude are equal but opposite. We incorrectly say they cancel. They do not. They appear to disappear as far as the current goes, and the current only thinks it sees the resistance, but in resonance circuits there's a multiplication of voltage across the inductor and or the capacitor. When X sub L is equal to minus X sub C, I is V times R. V over R. Voltage across the inductor is equal to that across the capacitor, just at different times. And the voltage across either is equal to the source voltage times the Q, where Q is X over R, the ratio of the reactance to the resistance. Higher the reactance, lower the resistance. The higher the Q, the higher the voltage multiplication. It's possible to put a relatively small voltage across that circuit, have high Q, and get a nasty shock off of it. 1 volt applied, if X sub L is the same as X sub C in 100 ohms, with R of 10 ohms, Q is 10, and the voltage across each is 10 volts. It didn't come out of nowhere. Think of it as increasing as the reactances appear to decrease. Here we have I is essentially a constant, K. The voltage across resistor is current through the series circuit times resistance. And V sub C equals V sub L at different times, which is much greater than V, by the factor of Q. When X of L is not equal to minus X sub C, comma, then the series circuit, ignoring the resistor, is either net inductive X sub L or net capacitive X sub C. With a series circuit of 100 ohms inductive reactance and minus 10 capacitive, the circuit becomes a net 90. The 10 is subtracted from the 100. And it's not subtracted just because there's a minus sign there. This isn't exactly simple algebra or math. We subtract the smallest to keep a sense of what's happening in the circuit, but those can be reversed. If the capacitive is greater than, it ends up being a minus 90. Yes, the sign follows it, but don't just blindly follow it as a math convention. It's important to understand what's happening in the circuit. Net 90 ohms, that becomes the impedance of the circuit. Since there's no resistance, the impedance would be 90 ohms. In a parallel resonant circuit, parallel LC with a series resistor, the resistor can also be in the inductor or capacitor branch. That complicates things quite a bit. It'll actually change the frequency, believe it or not. I read it in the book. I didn't quite believe it. I calculated, and sure enough, it does. The characteristic of a parallel circuit is that the voltage is the same across each component, but the current is different. And inverse to the series resonant, when the voltage is the same, the current is multiplied by the Q. Can get very high current. X sub L equals minus X sub C in the series circuit becomes minus X sub L equals X sub C, flipping the sign when we consider parallel circuits, inverted signs. X minus X sub L equals X sub C. Voltage cross resistor is 0 at resonance. I times R is 0. I sub L equals I sub C, which is I accelerated by the Q factor. There's the X sub L and X sub C in parallel. That's approximated by two parallel resistors. That's two parallel resistors. That's two parallel impedances, pure impedances, no resistance. They combine by a similar law as two parallel resistors. Invert each value, add them, invert them again. Same with reactances. Invert their values, add, invert again, although it cannot be done with simple algebra. In a parallel form, that's called admittance, which is the reciprocal of Z impedance. In the complex world, there's Z for impedance, Y for admittance. R is R. In the world of impedance, in admittance, it becomes G, or conductance. It's 1 over R. In a series circuit, R plus X equals R plus or minus JXL or JXC. In a series circuit, it would be R minus JX sub L, plus JX sub L, or R minus JX sub C. That's the complex impedance form. It's critical to note those cannot be added directly. They're different animals. R has no phase angle. Reactances have a very high phase angle. That can also be expressed in polar notation. In angular notation is R plus or minus J theta. You might see R with an angle of theta degrees, where theta is arctangent X over R, which is the arctangent of Q. The higher the reactance compared to the resistance, the higher the phase angle, approaching 90. If it's a purely resistive circuit, there's no phase angle. To add series impedances, for example, R10 plus J5, which is 10 ohms and 5 ohms inductive reactance, if we want to add R7 plus J11, and you won't see R written in these expressions, I put them in for clarity. It's understood, but if you've never seen this before, it may not be clear. R10 plus 5, R7 plus 11 means R7 plus 11 ohms inductive. To add them, we add the R's, R7 plus 10. We carry the J, the plus J, because they're both inductive, 5 plus 11, which gives a total of R17 plus J16. When we try to add it in the world of admittance, which is in the context of parallel, we have to invert that. To invert R10 plus J5 into an admittance form, recalling that admittance is 1 over Z, we express it as 1 over R10 plus J5. We can't do anything with that. We have to convert it to not being a quotient, not being a fraction. We do that by the method of complex conjugates, and you'll hear that discussed with regard to antennas. And this is what's happening. There are actually 2 ways to tune a feed point. It's not good, but it can be done. That's simply adding reactants, and then there's complex conjugates, and they are not the same. To go from R10 plus J5 in admittance and in impedance to admittance, we multiply it by the inverse correction. We multiply it by the impedance and changing the sign of the reactants. So we multiply 1 over R10 plus J5 by unity. And recall in math, multiplying something by unity doesn't change it. We can multiply that by 10 million over 10 million, and it doesn't change 1 over R10 plus J5. We flip the sign. R10 minus J5 over R10 minus J5, that's a quantity of unity. Then we do complex math. We multiply the denominator, R10 plus J5 times R10 minus J5, and in the numerator, R10 minus J5 times 1 doesn't change. Instead of going through the more messy multiplication, there's an easy way around this. It's a squared plus b squared. Notice in the denominator, it's always on the left plus J5, on the right minus J, or on the left minus J something plus J something. It always flips the sign. They're never the same. The result of that becomes R10 minus J5 over a squared plus b squared, where a is a resistive value and b is a reactive value, and it's always a squared plus b squared. Just take the numbers. 10 squared is 100, 5 squared is 25, add them together, 125, stick it in the denominator. That's done. No messing with it. Where a is r and b is x. Now to finally convert that away from a fractional form, multiply the correction, divide the numerator and denominator by a squared plus b squared, or 125, and the denominator goes away. That's not really useful here because it's implied that R10 minus J5 is times 1, but maybe if there was a 125 times R10 minus J5, the 125 top and bottom would cancel. That would simplify it. So it's just algebraic simplification. But don't make the mistake I did. You can't add R10 and J5. No way. The best source for understanding complex math is a paper online from lamar.edu. Extraordinary paper explaining complex math. Very, very good. Very important characteristic when trying to understand antenna graphs and tuned circuit graphs. X sub L is linear. There's a little graph, straight line. Capacitive reactance is a function of 1 over x. It is not straight. When we combine the two in a series resonant circuit, and you'll see this on an antenna graph, we see a fairly shallow line, a low slope. Under the line, it is always capacitive, no exception. Above the line, always inductance, no exception. Where they meet is apparently resonance. In a parallel resonance circuit, it has a asymptotic behavior, and L's and C's are flipped, and the impedances change extremely quickly. They try to go to infinity. And a more important concept yet, I've never found in any book, bandwidth is not Q. Bandwidth is a ratio of inductance to capacitance. It's called the LC ratio. There's an old Bliley crystal document that talks about it. We're normally taught to believe that bandwidth is a function of Q, but what if it's a very high Q, as in a crystal? That doesn't jive.